Okay, good morning to you all. Shall I make it full screen?
Yes, sir.
Is it full screen now?
Yes.
Okay, very good. Good morning to you. Today, we'll be discussing another topic. Okay, the other topic what we'll be discussing is material properties at cryogenic temperatures. Okay, how the material properties get varied at low temperature. This is what we will see today, right? Okay, now the plan of my presentation is to be something like this. We will just discuss about the various materials, properties at cryogenic temperatures, what sort of issues one faces when you use different materials. So we have to characterize suitable materials and unsuitable materials for cryo temperatures. Then we'll discuss about the various properties of materials at cryogenic temperature. Number of properties are there. For example, thermal expansion, and then mechanical properties like yield strength, fatigue strength, etc. Then transport properties, particularly relating to electrical and thermal transports, specific heat, thermal conductivity, then electrical properties. Then we come across another important topic called superconductivity, because some materials lose their resistance completely. That means the resistance drops to zero at a specific temperature called the transition temperature. That is characterized by what is called superconductivity. And there are also a number of composites which are being used for low temperature applications. So we will talk about also the composites which are useful for cryo temperatures. Okay. Composites are some new type of materials where you have a fiber and you have a resin, and then they form a composite. You can have different type of shapes and types of composite materials. So they become very useful for low temperature application. Okay. Okay, what sort of issues one faces with materials at low temperatures? First of all, normal behavior at room temperature, okay, is not the same at low temperatures. So what happens is the behavior becomes different at cryogenic temperatures. So you should really take care when you design any cryogenic system, because the property is going to change like this at low temperature. So there are many materials which become unsuitable for low temperature use. So, and such materials, they cannot be used at low temperatures. Okay. But in some cases, for example, the materials can turn into special materials and it can make them very useful. For example, if you take a material like, something like mercury, or let us say niobium, etc., they undergo a transition to become superconductors at low temperatures. So if it becomes superconductors, then they can carry enormous amount of current without any dissipation. So they become very useful for low temperature applications. But sometimes, the property changes may be such that the material can become brittle. So it is not useful at low temperature. But sometimes even the material become brittle is useful to process the material itself. Maybe I want to make a fine powder of the material. Then brittle material, when the material become brittle, it is useful. So low temperature processing can be useful for brittle materials. Okay. Now some changes, for example, may be also useful for processing. And what we will do in this lecture is to study the material property changes at cryogenic temperatures and what sort of applications they have, etc. We are going to discuss. Okay. Now let us see the selection of materials at cryo temperatures. Okay, what sort of materials we can select? First is, for example, all stainless steel, austenitic stainless steel. Grades are 304, 304L. 304L means it has low carbon content in 304. Then 316 and 321, etc. These are which are called the normal non-magnetic steels. But there are also magnetic steels, stainless steels, which are also useful at low temperatures. People use them for where there is a need for a magnetic property, then they use such material. For example, superconducting, let's say helium transfer coupling on the rotor, on the rotor shaft, you may need a magnetic material. The stainless steel of magnetic grade. Then aluminum alloys, for example, they are very useful. 6061, 6063, 1100, etc. There are a number of different alloys, and these alloys become useful at low temperatures. Then, for example, copper, oxygen-free high-conducting copper, OFHC copper, and then electrolytic grade copper, which is ETP, and then phosphorus deoxidized brass, etc., can become useful at low temperature. You can, for example, you can make a heat exchanger, or you can make, let's say, a sample holder, things like that is possible. Then it's also possible to use, for example, niobium and titanium. Niobium is used in superconducting RF systems, for example, niobium cavities. People use them for such purposes. But niobium become brittle at cryogenic temperature, so they have to be handled very carefully. Invar, which is alloy of nickel and iron, it is useful for making washers, etc., fasteners, that is essentially bolt nut arrangements. So they become useful for such purposes. And they are useful because they have low thermal coefficient of expansion. Then you come across indium. Indium is a metal, very soft material, and so it is useful as o-ring in cryogenic temperatures for sealing. It is between two flanges. If you want to seal, you can use indium as a sealing material. Okay. Then there are other materials like kapton, mylar. Okay, mylar is used in, the aluminized mylar. Okay, they are used in multi-layer insulations. Okay, they are used both for electrical insulation as well as thermal insulations. Okay. Then quartz, it is used in windows. Suppose I want to make an optical observation, then what I need is a quartz window. Okay. Then there are fiber reinforced plastics. Okay, FRP. Okay, fiber reinforced plastics. Specific grades are there, G10, G11, etc. They are useful for support structures. So what we will do is, we will anyway go through some of these things in detail, and then we come up with, we get an understanding of what are useful for loader. Okay, what are the unsuitable materials? Sorry. What are the materials which are unsuitable for low temperatures? For example, martensitic stainless steel. Okay, they undergo a ductile to brittle transition when cooled down. So you have to be careful when you are using this type of material. Okay, and then, for example, cast iron, it becomes brittle at low temperature. Carbon steel, it also becomes brittle. Okay, many times carbon steel is also used at 300 K vacuum vessels, and so in that case care should be taken so that the pipes does not become brittle, and it should not affect the main vacuum of the vessel, and sometimes it can fail. So you have to be careful if you use, for example, carbon steels for the outer vacuum jacket. Okay, and for example, rubber and most plastics, they all break. Okay, they actually crack at low temperature. Rubber, plastics, etc. For example, some of the exceptions are KLF. Okay, it's a brand name, and then UHMB, ultra high molecular weight polyethylene. Some of these things are used in cryogenic seat wall seats. Okay, So they are useful for that purpose. Teflon is actually a very useful material, but it has a lot of thermal coefficient of expansion. So thermal contraction is very high. So Teflon, if you want to use it, it does not become brittle. That's the advantage with Teflon. It is actually soft material. So, but it has a large thermal coefficient of expansion. Okay, so the contraction at low temperature will be pretty high, right? Okay, let's come to the material properties. First, we'll talk about thermal expansion. Okay, now materials, so if you apply heat, material expands. Similarly, if you do the reverse operation, instead of heating, you start cooling, then what happens is material contracts. Okay, so large thermal contractions can take place on materials which are cooled to cryogenic temperatures. Okay, what way it affects? It affects on alignment. Suppose I make an alignment of two components. Okay, at room temperature, they are all perfectly aligned. But suppose the same item is taken to low temperature and two materials are different, then alignment will be gone because thermal contraction for both the materials will be different. Then sometimes the development of interferences, gaps due to dissimilar material, large gaps can come. Okay. Then also what happens if you do not allow it to expand or contract, then a lot of strain will be there on the material and possibly it can even fail. Material also can fail. Okay. If it is a material like carbon, steel, and so on, sometimes it can even crack. Okay. Or it can become brittle. Then sometimes it can also impact on the wirings, instrumentation wiring. So such cases, it will become a problem. So normally thermal contraction is found to be maximum up to 77 K. From room temperature, if you keep contracting, the material contracts, then the maximum value occurs at between 300 to 77 K. But 77 K to 4 K, the contraction is significantly less. Okay. How does thermal contraction, or what is the reason for thermal expansion? Okay. Now, I don't know whether people have studied this. Okay. First of all, you can imagine the atoms are all arranged in a lattice. Okay. In lattice means there are fixed points. Okay. There are points where the atoms are located. And normally what happens, because of the thermal energy, then the atoms keep on fluctuating around their mean position. This is what is called lattice vibration. Okay, the atoms move about their mean point, right? Now, this vibration of the atoms depends on the temperature. More the temperature, more will be the vibration. But you see, the average position of the atoms, mean positions of the atoms is the same. Okay. Only thing what happens, higher the temperature, it will vibrate to a larger extent, right? But the amplitude will be higher. Just the amplitude will be more and more and more when you keep on increasing the temperature. But then the mean position is the same. Okay. What really happens is, but the atoms, the so-called potential energy. See, for example, if the atom is located somewhere here, then this is the mean position. So like this, it starts, amplitude will be like this. So this is what is called the normal harmonic potential. But what really happens is, because of the presence of interaction with various neighboring atoms, it is not anymore the unharmonic potential. For example, atoms potential will be unharmonic, not harmonic. Okay. So really, if you see, you can understand this better. If I put an atom here, it keeps oscillating. But then the mean position keeps on moving farther to the right. Okay, that means the separation keeps on increasing, the mean position. If I am able to supply sufficient energy to the atom, it may even get displaced. The atom can simply go out, right? So this is what is happening. Okay. So this is what is called unharmonic potential. So this anharmonic potential is responsible for the expansion by the application of heat into the system. So when you heat, the atoms vibrate more and more and more. Okay, the lattice vibration increases, and then because of the anharmonic potential, the the average mean position keeps shifting. So that's why you have a thermal expansion, right? That's what happens. Now, actually, there is a dimensional ratio which is called gamma, which is known as also Grunetian constant. This value is supposed to be same for all materials, all solids. So the gamma can be written as V alpha divided by K into CV. Okay, here V is the volume, alpha is the thermal expansion coefficient, K is isothermal compressibility, and CV the specific heat constant. So once we know this value is constant for all solids, so you can estimate, for example, what sort of thermal expansion from one solid to another. So if you know a couple of parameters, then you can determine the other parameters, right? Okay, like this. Now, how do we define the thermal expansion coefficient? It is defined as the change in the length for unit degree change in temperature to the original length. That is dl by dt by the total length L. So that is the so-called thermal expansion coefficient. Okay. Now this thermal expansion coefficient actually varies with the temperature. For example, you have the temperature is plotted on the x-axis and the thermal expansion coefficient is plotted on the y-axis. I mean, assume this is for some typical material. Okay, if you keep decreasing, the value of alpha keeps on decreasing. And then alpha is independent of temperature at high temperatures, whereas at low temperature, alpha is nearly constant and it has almost zero slope when it reaches 0 Kelvin, right? So for practical work, the integral thermal expansion is more useful. That is how much it is over a particular this thing, etc. Now, for example, stainless steel, the thermal expansion, delta L, change in the thermal expansion value to the original length, delta L by L. Suppose I want to evaluate from 300K to 100K, it is 296 into 10 minus 5. You see, if you compare this with that value between 100 to 4K, look at this. This value is very small, only 35. Whereas the major thermal expansion or thermal contraction occurs in the 300K to 100K range. Okay, copper, a little higher than stainless steel, 326 into 10 raised minus 5. This is between delta L by L value between 100 to 4K will be 44 into 10 raised minus 5. Aluminum, little more. Then iron is almost same as steel, but much less. Invar, small. Then brass, 340. Epoxy fiberglass, you see, it is 279. Almost like stainless steel, right? But this is about 47 10 raised minus 5. Titanium is one of the very useful material for low temperature application. That is 134 10 raised minus 5. But the value of delta L for 100K to 4K is 17 into 10 raised to minus 5. Okay. So please remember that thermal expansion coefficient is an important factor, and the integral thermal expansion is really useful for estimating how much thermal contraction that will happen in a system. Okay, there are some standard tables are available, and there is a website called NIST, National Bureau of Standards for Materials. So this is available. NIST website is available where you can get the thermal expansion coefficient, particularly linear thermal expansion delta L by L. Okay, and that is available, okay, with respect to temperature. So you can just get, these are the integral thermal expansion values. So you can see here different materials and from 300K to 0 Kelvin. So Invar, Pyrex, okay, some particular unalloyed steel, nickel, contrast it, stainless steel. So stainless steel is number 6. Okay. Then copper, German silver, brass, aluminum, silver, solder, indium, and then mercury, ice, araldite, perspex, nylon, Teflon, etc. Different materials have been plotted. But what you notice here is Teflon is having a very large thermal contraction. See here? That's the largest. So Teflon is actually having a very large thermal expansion, or in other words, thermal contraction. So if you are using Teflon, it will shrink a lot when you go to low temperature. Please understand. So the defining design of a cryogenic system should really take care of all this thermal contraction of the materials. That's very important to take. Okay. So what is plotted here is delta L by L divided by 0 by 00, which means it is not just percentage, it is 1 by 1000. Okay, so I would like to point out here, for example, this is roughly about -3. Okay, you take stainless steel, 1 meter length. Okay, how much it is going to contract? 1 meter length is 1000 millimeter. It is going to contract by about 3 millimeter in, and when you cool from room temperature to low temperature. So it's about 3 mm, that is what is going to contract. Right. Okay, there are, I don't know whether I have played this video and so on, but it may not be necessary at this point. But if it is possible, I'll try to play it. Okay, what is the use of thermal contraction? First of all, joining two dissimilar materials. Suppose I want to join two metals. Okay, I want to do this. Then you can use what is called shrink fitting. They are useful for fitting the bearings into the housing, and you can do this process. There is a video here, but I'm not sure whether it will play. If it doesn't play, it doesn't matter. Okay. Okay. Maybe we would have seen this video in the very first lecture. Yeah, it is playing. I'm really surprised. Okay. So, for example, you have a brass part, you have an aluminum part. At room temperature, the aluminum part will not go into the brass part. Okay. Why? The aluminum part has got a slightly excess dimension compared to the brass hole. Okay, he is trying to show you that he is not able to put it inside, right? So what he is going to do, he is going to cool the aluminum part in liquid nitrogen temperature. Okay, so that's what he is doing. Now, after cooling, he will wait for some time. Just wait a minute for a minute. Sorry. Okay, now you see, he has been able to join the two materials together, and then it has now become a single material. So this is what is done. So when you try to fit two different materials, one of them is cooled, so it shrinks. So the dimension now matches to that of the other one. So therefore, two materials are now joined together. So the upper photograph shows you the fitting of a bearing. Okay, the actual the shaft is fitted with the two different materials. So a bearing is fitted onto that. You see this material now, it's tied together. You cannot separate them in any way. If you want to separate, only way is to machine off one part of the component, so that you cannot save both of them. You have to save only one of them. Okay, let's look at the mechanical properties. If you look at the mechanical properties, the material strength tends to increase at low temperatures. As long as there is no ductile to brittle transition, material strength increases at low temperature. So, but still, on the design, what normally people do is they use the 300K values, or using it for a conservative design, because it is a slightly smaller value. So that means you are going to use that system for, for example, maybe support something. Okay, so the material strength is very important for that. So for such cases, the 300K values will be actually making sure that you have a better performance at low temperature. Remember, all the systems start out at 300K and also return back to 300K. So this is what is called thermal cycle. Thermal cycle means I start with 300K, I keep on decreasing the temperature to whatever lowest value, then come back again to 300K. So this is what is called thermal cycle. So the material has to undergo thermal cycles. Many times the thermal cycling is very important to make sure that the material performs well. Okay. So again, the lookup values for materials should be considered. You can take it from cryogenic database and so on. It is possible to do that. Okay, I am now just showing you the yield strength, for example, for different materials. So what is plotted here is on this graph, yield strength in megapascal on the y-axis and temperature in Kelvin on the x-axis. So you have different materials. Well, now you can see here the strength of Teflon is the smallest. Okay, it's very low. That means it cannot, if the strength for this material is very, very poor, but at low temperature, it has a slightly better performance compared to room temperature. That means it will yield much more at room temperature, whereas at low temperature, it has a little resistance to yielding. So yield strength is somewhat higher. Okay. If you look at various other material like aluminum, beryllium copper, monel, titanium, stainless steel. For example, typically number 5 is stainless steel. Okay, you just see here. So the strength of all the materials, yield strength of all the materials gradually increase at low temperature. They gradually increase at low temperature. So it becomes useful. If I use a material at room temperature, it will certainly perform better at low temperature in terms of yield strength. Okay, that's what will happen. So here we have shown you for aluminum, number 1. Okay. Then beryllium copper, number 2. Then you have monel, number 3. Okay. And titanium, number 4. Okay. Titanium has increases strength considerably at low temperature. Then stainless steel, number 5. Okay. Carbon steel, nickel steel, and Teflon, Invar, etc. So in all cases, as you go to low temperature, yield strength increases. Okay. Let's come to ductility. Ductility means the material become ductile. That means it's able to pull apart. Okay. But the ductility of the material normally decreases at low temperature. It is actually slightly less at low temperature. Ductility of the material decreases at low temperature. For example, if you take carbon steel, it undergoes a ductile to brittle transition. So carbon steel here is number 6. So you can see here this curve goes down and there is a sharp transition around 100K. So it undergoes a ductile to brittle transition. And therefore the material will become brittle. If you cross 100K, material become. That's why we said carbon steel cannot be used for low temperature applications. Right. Okay. But if you look at the other materials, in most cases, material ductility decreases with the decreasing temperature. Okay. You can consider, for example, number 5, okay, stainless steel, or let's say number 1, which is aluminum, etc. Okay, except for the carbon steel, which undergoes a transition. Okay, other materials, the ductility decreases. Now let us look at the fatigue strength. What is fatigue strength? Fatigue strength, it is the stress required for a failure after a number of cycles. Okay, so that is what is called fatigue strength. And this fatigue strength again improves at low temperature. That means if the material is operated at lower temperature, it can do more number of cycles for the given load. Okay, it is possible to use same material at low temperature and it will perform better. Okay. Now we can see here different material. Number 5 is stainless steel. And number 4, titanium. Okay, number 2, again, there is a certain improvement here. Then number 1 is, what is that? T4 aluminum. So you have a behavior of this type. Okay. Now, if you want to improve the performance of the materials at low temperature, there is something called cryogenic treatment. So this is called cryogenic treatment of metals. It is a process which modifies the microstructure of materials to enhance their performance. Okay, what happens is normally if you take steels, normally after the heat treatment, steels are left with certain percentage of austenite. But this is not transformed to martensite. Some amount of residual austenite exists, okay, and it is not 100% converted to martensite. Martensite is really a very strong component, okay, compared to austenite. Now, this residual austenite is called retained austenite or residual austenite, RA. Okay. Now, what does the cryogenic treatment do? The cryogenic treatment actually transforms the residual austenite to martensite. Okay. This is what 90% of the steel already is desired condition. The martensite is a very much desirable condition. Okay, but there is some amount of austenite which is left over. If you do a cryogenic treatment, whatever that is left over will also be transformed to the martensite. Okay, so the material becomes very strong. Okay, what happens is during a cryogenic treatment, all the voids, imperfections, etc., in the steel microstructure gets eliminated. Okay, in our center, we have developed this cryogenic treatment setup. It enables a gradual cooling of the sample from room temperature to low temperature, then soaking at the low temperature, and then warm up back to room temperature. So now I will just show you the detail of the cryogenic treatment cycle. Okay, the cryogenic treatment cycle will be, you have a material at room temperature, then it immediately you put it in a chamber or something, you start cooling down, then the material gradually decreases in temperature. Then this is the cryogenic temperature. It can be liquid nitrogen temperature or it need not be. It can be also at a higher temperature. So it is possible to have a cryogenic temperature. And then afterwards, after a particular time period, then you remove the material, allow it to gradually warm up. Okay, you can do an assisted warming or a conventional warming. Then in that case, the material comes back to room temperature. So this is what really happens. So you can have what is called so when you start with the material at 300 K, you have what is called a cool down period. Then there is something called soak period. Then you have the warm up period. So this is exactly what is called the cryogenic treatment. Okay, and there is an experimental setup which has been built by one of my colleagues, Mr. Durgesh Nordic. Here you can see the experimental setup. So you have a storage diwar for a cryogenic fluid, which is a liquid nitrogen vessel. And from there, the liquid nitrogen is pressurized and allowed to come up. Then it tries to enter a vessel in which various components are located. Okay, the material which you want to treat, it is enclosed in a chamber here. This is the chamber in which it is enclosed. It's actually sealed the chamber. It has certain inlets. Okay, I'll come back to this. So the liquid nitrogen actually comes over and enters an upper chamber. And there is also a fan. The fan, when it runs, it makes sure that the vapors are completely distributed and it cools this complete vessel. The entire vessel gets cooled. Okay, once it cools the entire vessel, then you can have the soaking period. Okay, the period at which so the material which you want to, let's say, cryogenically treat, they are located in this particular chambers. Trays, so many trays are there. No? You have to keep them in the trays. Okay, then this can be completely instrumented. So you can take temperature measurements at regular intervals, and they are all completely data collection is done. And in the data collection will now tell you what sort of the cryogenic treatment cycle the materials have gone through. Okay. Now, this is the schematic, what you see on the left-hand side, and this is the practical experiment system. And this use a board wherein all the electrical controls, etc., are arranged. Okay, now what is the result of cryogenic treatment? So, for example, if you start an untreated tool, the wear is higher. It's about 88. Whereas if you do a cryogenic treatment, the wear is only 59. So which means the percentage, there is a percentage improvement on the material because of the cryogenic treatment, and that's almost about 33%. Coming to frictional force, the untreated tool is having 10.5, whereas cryogenically treated tool is having a lesser quantity, which means that due to the frictional force, okay, the material is a little more strong. Okay, that's what really happened. Okay. Now we are going to discuss what is called transport properties. This transport property means these are the properties which are useful for transfer of thermal or electrical energies through the solid, right? Okay, let's come to the heat capacity of the materials, what is called specific heats. We understand what is specific heat. This we have discussed even earlier, but I'll try to explain now. Now, if you take a solid, it is nearly at atmospheric pressure and at room temperature. The solid has what is called a specific heat. What is specific heat? Specific heat, the heat content, okay, the heat required to raise the temperature of a sample by 1 degree centigrade, and that too per unit mass of substance or per gram. Okay, if you have to use SI units, you have to say it is the specific heat per unit mass, which is kg. Okay, and specific heat, the heat content is always expressed in joules or calories, etc. Now, this specific heat at room temperature is nearly a constant for all solids. It has a value of approximately 3 times R. Okay, it is 3 times R. R is universal gas law. Okay, now if you take cryogenic temperatures and you start the value at room temperature, the specific heat keeps on decreasing, gradually comes down, and then ultimately the specific heat goes to zero at absolute zero of temperatures. That's what you normally see. Okay. What is the meaning of decreasing? Specific heat decrease with the decreasing temperature. What does it help? In what way it affects? It has two important effects. One is there is a systems normally cool down as they become lower in temperature. That means they go faster cool down because the heat content is now smaller. The specific heat is not there. So therefore, suppose I try to use a certain amount of cooling power only available, then after it crosses a particular temperature, then the cool down is very fast. They keep on decreasing much faster. And on the other hand, it also happens the other way, because specific heat is small, and that means the heat content of the material is small. So a small quantity of heat that is added, it will automatically suddenly raise the temperature of your sample. That is, high temperature rise will be there. Okay, now let's come to the condition. Where does this heat energy stored? The specific heat energy, where is it stored in the solid? Okay, they are stored in two places. One is what is called the lattice vibration. Another one is the electrons. So this energy is stored in lattice vibration, and secondly, it's also stored in electrons. So now if you understand this, okay, how the temperature dependence of specific heat of solids happens, then you can explain this in terms of the lattice vibration and electrons. And in fact, this has been done by quantum mechanics, okay, postulates. This has been done by quantum mechanics, early quantum mechanics, and this is actually an early victory for quantum mechanics because they were able to explain the behavior of specificates of solids using this postulate, quantum mechanics postulates. Okay. First, let us concentrate on the lattice contribution. What is lattice contribution? It is the contribution to specific heat by the lattice. So what is the lattice consisting of? Lattice is having set of atoms which are lying there, and there is a motion about the mean position of all the atoms. So the lattice contribution to specific heat is how they are. Okay, now if you take a solid at constant pressure, what is specific heat? Specific heat is the change in internal energy to change in temperature, du by dt. That's what is specific heat. Now, what is U? U is nothing but the total energy of all the solids, all the material in the solid. Suppose I take, let's say, a unit, let's say 1 mole of, if I take 1 mole of a solid, okay, 1 mole contains Avogadro number of atoms, 6.023 into 10 to the power 23 number of atoms are present in 1 mole. Now, if I take 1 mole of atoms, then what's the total energy? The energy content is, first of all, depends on temperature. It doesn't depend on any other parameter. So we can write 3 by 2 kT is the energy per molecule or per atom. 3 by 2 kT is the, we'll better consider a monatomic solid. So then you have 3 by 2 kT. And if there are n atoms, n is the Avogadro number. If you multiply by the n, then it is 3 by 2 nkt. Okay, what is n into k? N into k is nothing but r. We can write it as 3 by 2 r or t. That is your energy. Now, what is Cp? Cp is nothing but you have to divide this by, you have to divide by, you have to take du by dt, you have to calculate. That is nothing but 3 by 2 r. Okay. But you see, it is 3 by 2 r if you assume only potential energy or only kinetic energy, but you have to take both. So if you take both of them, it is nothing but 3r. U is equal to 3rt. So du by dt will give you 3r. And so this is the value predicted by the Dulong-Petit's law. So all solids should have a constant specific heat at high temperatures. Okay. But this certainly does not depend on, does not take into account of the quantum effects. And therefore, this value is okay at room temperature. Okay, what happens at low temperature? As you keep on decreasing the low temperature, then Cp keeps on decreasing, comes down, comes down. How do you explain this? Einstein explained this. He said the atoms now vibrate in quantized frequencies, that is specific frequencies. The atoms will now oscillate. Okay, what is the specific frequency? It is nu. It cannot vibrate in all frequencies. It can vibrate only in specific frequencies. Okay, he said it has to vibrate, like for example, suppose the vibration frequency nu, then it is n plus half into nu h nu. That's the energy that it will have, internal energy. So now these specific frequencies can be different modes. You can have different modes of frequencies. That is nu, okay, say half nu, half h nu, 3 by 2 h nu. Like that, you can keep on increasing. That is, the frequencies can keep on. That is a base value along with its, let's say, multiples. That's what it can have. So Einstein said that the atoms vibrate in quantized frequencies. So this explained the temperature dependence of specific heat. Okay. But it did not explain completely the results. Later on, Debye actually proposed a theory which accounts for the fact the atoms in a solid, or they are not independent, okay, and they certainly they oscillate at a particular frequency, and only certain frequencies are possible for the solid. So this theory was proposed by Debye. So Debye theory gave what is called the lattice specific heats of solids, and this lattice specific heats of solids is given by this relation: C is equal to 9 into R T by theta to the power 3, 0 to x max e to the power x, x to the power 4 divided by e to the power x minus 1 whole square multiplied by dx. Okay. So you might integrate this particular value. And here, what is called theta is what is called the Debye temperature. Now, if you look at the values at 300 K, the C is approximately equal to Tr, which is based on the Dulong specific heat. That's what we said, no? The value should be equal to 3R. Now, if you go to low temperature, what happens is, you see, if the temperature goes lower, suppose assume that the temperature is less than 1/10 of the Debye temperature, theta, then the specific heat now will vary as T cube. So lower temperature means it varies as T cube. That means it keeps on decreasing, and then becomes more or less a constant. That is why the specific heat varies with decreasing temperature. So this is the proposed by Debye. And now you see, we can see here the Debye theory accounts for the lattice specific heat of the solids. Okay. So we said, if you remember the discussion in the beginning, we said specific heat comes from two parts. One is the lattice vibration, then you have electrons. Now, what about electrons? The electrons' contribution to specific heat in a metal happens. The thermal energy is also stored in free electrons of metal. Now, the quantum theory shows that the electrons have only well-defined energies. It cannot have arbitrary energies. Only a fraction of the total electrons can be excited to higher states and can participate in specific heat. So, but it can also be shown that Cp of electron is equal to G into T. Okay, where G is some constant, so it is directly proportional to temperature. So now combine these two. What we have said there is a lattice specific heat, there is a specific heat due to electrons. So if you combine these two, the total specific heat variation at low temperature can be shown as C is equal to AT cube plus BT. A and B are constants. So there is a T cube term, there is a T, there is a linear term, there is a cubic term. Okay. Now, one of the things we can see is the contribution due to electrons is important only at temperatures less than 4 Kelvin, because it's a term which goes as linearly with respect to temperature. Okay. Whereas the other term goes as T cube. So the higher the temperature, the effect of AT cube will be shown much more significantly compared to PT. Now, paramagnetic materials and other special materials have what is called anomalous specific heats. Okay, we don't have to worry about that. Okay, but in any case, if you are going to use a material for low temperature application, you should find out what sort of property it has towards the specific heat. If you are going to look for raising its temperature, etc., etc. Now, this is the behavior of most of the common materials. So, specific heat is plotted on the y-axis and x-axis the temperature. You can see the different curves. There are specific materials given 304 stainless steel. Then you can consider brass, okay, copper and zinc. That is the combination gives you brass. Then comes monal, and then you have the aluminum. So you can see the behavior of the curves. They almost behave in the same manner. But what you notice is that at low temperature, they all have the same behavior of T cube. And as you go towards zero, the slope is almost nearly horizontal. The slope is nearly constant value. Okay, zero slope. Okay. Now, if there are anomalous specific heats, that is, if there are materials with anomalous specific heats, then they become useful at low temperatures and for building up regenerators. Okay. Now you can see here the anomalous physics for holmium copper, etc. So there are different materials which can be useful for low temperature. So here you see, if you are looking for if you consider a regenerator material and so on, then what happens? The heat has to be kept inside the material in one part of the cycle, and then heat has to be collected in another part of the cycle. So obviously, there is a need for increased specific heat on the material, on the regenerator material, which is used for low temperatures, okay, as a regenerator. Now, the reason why there is an increase in specific heat is because, for example, here, holmium copper, erbium nickel, erbium-3 nickel, and so on. Now, these materials have got increased specific heat because of what are known as the magnetic transitions which appears, and therefore material become useful at low temperature because of the enhanced specific heat. Okay. Let us come to the thermal conductivity of solids. What I will do is I will take a break right now, maybe about 5 to 6 minutes. Then we can come back and then we'll start the class. Is it okay with you? Hello? Rahul?
Yes, sir.
Is it okay? Now shall we take a break? What is the time now exactly?
10:53.
Okay, 10. We'll assemble back at 11 o'clock. Okay?
Okay.
Just come back at 11. Okay, bye. I'll stop here. We'll come back. Hello?
Yes, sir.
Should we start?
Yeah.
Is it okay?
Okay.
Okay, welcome back. Now we will discuss about the thermal conductivities of solids. Okay. Now, how do you define thermal conductivity? Thermal conductivity is is defined by a factor K, which is dependent on temperature. So we know the heat transfer is directly proportional to the surface area. It is inversely proportional to temperature gradient. So therefore, we can write Q is equal to minus KT. K is the thermal conductivity, and area of cross section of A into A of X into dt by dx. So you can write Q is equal to Ka into T1 minus T2 by D. This is a very standard formula which we also know that this is the so-called thermal conductivity of the material. So what does it signify? If the thermal conductivity is very large, then large amount of heat transfer happens from one end to the other. Okay. If the thermal conductivity is small, then less heat transfer happens. So for example, you can classify the material as good thermal conductors and poor thermal conductors. Good thermal conductors will make sure that the material will have uniform temperature throughout, whereas poor thermal conductors will make sure that one end can be very hot, whereas the other end can be nearly room temperature. Okay, but the K of T, K, the thermal conductivity, does depend upon temperature. Because it depends on temperature, its temperature dependence must be considered while calculating the heat transfer behavior. Okay. Okay, now similar to what we discussed earlier in terms of specific heat, we can also consider how the thermal energy is transferred. Okay. How the energy is transferred within a material. Okay. Now we can consider that. In the earlier one, what we saw is how the energy gets stored. Now we are going to consider how the energy is going to be transferred. So they are transferred by, again, the same lattice vibrations or phonons as well as electrons. So in a reasonably pure metal, the contribution of conduction electrons really dominate. Okay. Now there are conduction electrons. No, we are going to talk about lattice vibration and conduction electrons. So we'll consider the conduction electrons part. So there are two scattering mechanisms for the conduction electrons. The one is the impurity, and then another is phonon. Okay, see, electrons now try to move the energy. Okay, the heat energy is picked up by the electrons, and then they go into the material and then try to transfer the energy. But there is impedance for this, for the transfer of energy. What is the impedance? It is due to impurities in the material. Okay. Then there are also phonons, that is the lattice vibrations themselves, which do not allow the energy to be transferred. So this impedance, or what you can say is scattering mechanisms. So you can say, in other words, it's a thermal resistance. The thermal resistance due to impurities, you can write W0, WO is equal to beta by T. That is 1 over T. Beta is a constant. So it is inversely proportional to temperature. Whereas the scattering due to phonons, it is actually, it's constant multiplied by T square. That is the sort of energy. Okay. Now, if you take these two terms into account, the thermal resistance for the, what shall I say, heat transfer through the material is thermal resistivity has the form W total is equal to alpha T square plus beta by T. So this is of this form. Okay. So next, what happens is, if you look at the thermal conductivity of metals by electrons, then you can see here, for example, the resistivity due to then it has two parts. One is the impurity scattering, it is 1 over T. So it falls like this. Okay. And then the other part is lattice scattering. It is lattice scattering actually increases, but is proportional to T square. So one term is 1 by T, another term is T square. So if you consider these two into account, then you find that this is the way net. If you add up these two, this will be the total resistance. What about conductivity? Conductivity is inverse of resistance, right? Conductivity. So if you just take the inverse of this, then it will look like this. This will be the conductivity. So low purity material, then somewhat improved purity, then you have the highest purity material. It will go like this, right? So this is the behavior what we'll have for the materials, right? Okay. Now, you can typically see, for example, this sort of behavior in the case of copper. Now, what about the heat conduction by phonons in the metals? Okay, we also said, no, it is both by phonons as well as electrons. The electron parts, whatever we have seen now, what about the phonon? Phonon heat transfer actually is a behavior which is proportional to A by T square. W is equal to A by T square. And normally this is neglected. Okay, you don't consider them unless you go to extremely low temperature where T is very small, so T square becomes so small that this factor comes into existence, right? Okay. Now the thermal conductivity of data for metals are available. So you can see here the thermal conductivity behavior. So this, for example, I don't know what is it, copper. So the copper, for example, you have this behavior of this type. Okay, there are other materials. The materials like stainless steel, and then phosphor bronze are shown here. And then manganese also is shown here. So I think the first 2 graphs are for copper. And you have a copper of RRR. Okay. RRR means residual resistivity ratio, RRR. Okay, these values are, the behaviors are, for example, high purity material goes up and then goes down. So x-axis is temperature, y-axis is actually the y-axis is in terms of thermal conductivity values in watts per meter Kelvin, right? Okay. I'm sorry. I went back to the other screen. 1 minute. I want to make it full screen. Yeah. Okay. You see it now better? Right. Okay. So there are RRR value 100 and RRR value is 20. What is RRR? Residual resistivity ratio. So it is the value of the resistance at 4 Kelvin and to the value of resistance by 300 Kelvin. So at any other temperature. So 300K divide by the 4K value, that is value ratio is 100 or it is 20. So 20 means the material is very pure, right? So the residual resistivity ratio value will determine the performance of these material thermal conductivity values, right? Okay. Now people do not use just the thermal conductivity, but rather they use what is called thermal conductivity integrals, because thermal conductivity itself, it depends on temperature. And suppose you want to have from one temperature level to another temperature, then you can always integrate from one particular temperature to another temperature, the thermal conductivity integral with respect to dt. So they use that into picture. So therefore, heat conductivity equation can now be rewritten as Q is equal to minus G into theta 2 minus theta 1. G is actually the geometrical factor. It depends on the area and then the length, whereas area of cross section and the length, and theta represents the thermal conductivity integral. So you can see here the geometrical factor is given by this formula and the thermal conductivity integral value is given by this formula. Theta is equal to 0 to Ti K of T into Dt, right? So now the thermal conductivity integrals also are given for different materials, and these data is taken from Handbook of Cryogenic Engineering by John Wiesent. Okay, and he is the editor for this particular book. So they are very useful information available for different materials for low temperature. Now, thermal conductivity integral also can be done for metals or non-metals. And obviously, you will see non-metals will have low thermal conductivity compared to metals. So therefore, the integral value also will be very small for non-metals compared to metals. Okay. Now let's come to the electrical properties. Now the electrical property is very simple. We use what is called the Ohm's law. The electrons transfer the current flow, the rate of flow of current is nothing but the charge flow with respect to time is nothing but your current. So Ohm's law gives you what is called the basic equation. The voltage developed across a path, or suppose I apply a certain amount of put a voltage on the system across the two terminals of the material, then a current can flow depending on the resistance. So this resistance value is proportional to rho L by A. R is equal to rho L by A, which means it is proportional to the length, inversely proportional to the area of cross section. And rho is what is called electrical resistivity. Okay, one is resistance for the material, another is the resistivity. It is for unit length of material at unit cross-sectional area, right? Now, conduction electrons normally carry the current and the current flow. There are basically two scattering mechanisms for this. Okay, again, as before, as we have done in the case of thermal conductivity, here also the scattering is by the phonons, and the scattering is also by the impurities or maybe defects, dislocations, etc. Right? Okay. Now, for temperatures less of the order of D by temperature, we have seen the D by temperature where the that value, the specific heat keeps on decreasing. The D by temperature we have seen. The phonons, for temperatures of the order of D by temperature, phonon scattering dominates, and the resistance is simply proportional to temperature. For temperatures much less than the D by temperature, impurity scattering dominates, and the resistance is nearly constant. Okay. Now, in between these two regions, say T is of the order of, I think it is theta by 3. It is not Q by 3, it is theta by 3. R is proportional to the power minus 5 for metals. So residual resistivity ratio is an indication of the purity. I told you about what is RRR? It is R at 300 Kelvin divided by R at 4.2 Kelvin. So for example, here, copper, the resistance values 30, then 100, 300, then 1000, then 3000, 10,000, 30,000, etc. As you can see, as the electrical resistance resistivity ratio keeps on increasing, the material becomes purer and purer and purer, right? So the higher the purity, the lower will be its resistance, or higher will be the conductance part. So this is, I think, for copper. You see copper, whose resistivity ratios keeps on varying. Okay, what are the advantages of using this? One advantage is the variation of resistance can be useful as a thermometer. So we have come across what is called the platinum resistant thermometer, which means the resistance varies with the temperature, and so by measuring the resistance, you will be able to determine what is the temperature. So this can be used as a thermometer. So for example, if I take PT 100, which means at 100 ohms of resistance value at 273 Kelvin, or in other words, 0 degree centigrade. PT 500 or PT 1000 are the different resistance values that are normally available. You can also use other materials. For example, amorphous metal materials or semiconductors, etc. They can also be used for temperature measurement, but their resistance values completely are different. For example, they have an opposite behavior. See, in the case of metals, you normally see the resistance decreases with the decreasing temperature. You see, it starts from here and keeps on decreasing. Whereas in the case of non-metals, sorry, see germanium, for example, the resistance value increases with the decreasing temperature. Okay. And I think ruthenium oxide sensor resistor, for example, it gives resistance value, how it varies as a function of temperature. Resistivity at germanium is quite nonlinear, typically increases with the decreasing temperature due to the fewer electrons in the conduction band, whereas also for ruthenium oxide, the behavior is very similar. Okay, now this leads us to something very interesting topic, which is called superconductivity. Okay, what is superconductivity? We are going to discuss this. If we are not able to complete whatever we are telling today, we'll discuss it again once more in the next class. Okay. Okay. See, when we are studying the resistance variation with the temperature, you find for some material, the resistance suddenly drops to zero at a specific temperature. This temperature at which the resistance suddenly drops to really zero is what is called the transition temperature or superconducting transition temperature. I think we have already seen this as one of the milestones. In 1911, Camelingonus, when we were studying in mercury, he found that there is a sudden transition. The resistance went below 10 raised to minus 5 ohms in his mercury, sample. So there was a superconductivity observed, the Camelingonus, and this temperature at which the resistance drops to zero is what is called the transition temperature. Okay, and the transition happens in some metals and alloys, etc. Okay, and there are different temperatures at which the transition happens. Okay, so you can see, for example, what is the advantage of such a thing? Now, the advantage would be, so the temperature at which the material transits to zero, it suddenly resistance turns down to zero. That temperature is called the critical temperature of the material. Okay, what are the advantages of this is, so for example, the material will try to, the material will now become, whenever your current is passed, normally a voltage is developed across the material. Now, if the material does not have any resistance, then there cannot be any voltage developed across the material. So no voltage drop will happen across the material. So in other words, there cannot be any dissipation of electrical energy, or in other words, the current will not diminish with time because the resistance is zero. Okay. Not all materials can become superconductors. Okay, but there is also another interesting phenomena that happens along with just the resistance going to zero. The material also tries to expel the magnetic field which is present there. So you have an external magnetic field, then the material will try to expel the field. It will act as a diamagnet. Okay, so any superconducting material can also be a perfect diamagnet. Okay. See, there are a whole lot of materials which are available, but not all materials are superconductors. And I think here, for example, the typical critical temperature and critical field values are given for type 1 superconductors. So we will select some of them, aluminum, etc., 1.2 Kelvin, or let's try to come to some reasonable temperature. Mercury, its alpha phase is 4.2 Kelvin. And let us try to see. No, I'm not seeing anything. So most of the materials, the values are very, very small. Okay. The best value is 4.8, which is lanthanum. And alpha phase is 4.8 and beta phase is 4.9. Okay. Now, they have not listed out the niobium, etc. Here in this table, So the niobium has a value close to 9 Kelvin or so. So we'll see this. Okay, what happens? First we have seen there is a transition temperature. That temperature is called the critical temperature. The critical temperature, the temperature below which the resistance is zero suddenly, and then that means the material becomes superconducting. Now, there is a parameter called there are two. First parameter is the transition temperature. The second parameter is the external magnetic field, or we can say the critical field. Okay. And the third parameter is the critical current, how much current that it can take. Okay. The third parameter in superconductivity is the critical current. If the critical current exceeds, then superconductivity breaks down. So if we exceed the critical, so for example, I have a material, the material becomes superconductor. There is no magnetic field applied. Now what you do is you apply an external magnetic field. Then the external magnetic field will try to destroy the superconductor. Okay. So this magnetic field, so there is a critical field at which the material, below which only the superconductivity exists. Right? Okay. This is the second parameter. The third parameter is what is called the critical current. You pass a current through the material, then the current flow induces a magnetic field. Okay, it causes a magnetic field. Now, because of this magnetic field, the material, will turn to normalcy. That is, from the superconducting state, it will go back to the normal state. Okay, because of this current flow. Because when the current is flowing, then it generates a magnetic field, and that magnetic field, when it exceeds a critical value, then the material turns normal. So the going normal from the superconducting state is called the quenching of a system. The quenching of. Now, if you have a magnetic field, if you have a magnet built by a superconducting wire, then the magnet quenches, then it means it is going from the superconducting state to the normal state. So then now there are three parameters. The first parameter is the critical temperature. The second parameter is the critical flux. The third parameter is the critical current. Okay. Now there are two types of material. The first type material is what is called the type 1 superconductor. Then there is a second type of material which is called type 2 superconductor. Okay, what is the difference between the two? Suppose I take a material and then gradually reduce its temperature. At a particular temperature, the entire material becomes superconductor. At a particular temperature, the entire material becomes a superconductor. Completely. This is what is called type 1 superconductor. Now, there is also another type of superconductor which is called type 2 superconductor. So you keep on reducing the temperature. Yes, it comes down. First, at a particular temperature, the material, a part of the material starts becoming superconductor. It is not, the rest of the material is all normal, but a part of the material becomes superconductor. Okay, what happens? You keep on decreasing the temperature further. Then at another particular temperature, the entire material becomes superconductor. So in other words, the material becomes superconducting, okay, but it is a part of it is normal, a part of it is superconducting. Okay. So therefore, there are two critical fields for this material. The first critical field, the material starts becoming superconducting. The second critical field, what happens? The entire material now becomes the complete superconductor. Okay, now HC1 may be the low end of the magnetic field. HC2 is the high end of the magnetic field. So at HC2, the material starts becoming superconductor, and then at HC1, the entire material has become. So between HC1 and HC2, then you have what is called the mixed state. Okay, of the mixed, in this mixed state, the bulk of the material remains superconducting. And such a material is called the type 2 superconductor. There are a number of materials, type 2 superconductors. For example, type 2 are mostly alloys. Niobium is a type 2 superconductor. The type 2 superconductors orders have magnetic higher critical fields, and they are very useful for the applications. Okay, they become very useful for application. Now you see here the Large Hadron Collider niobium titanium wire, and we can very clearly see here there are three parameters which are shown here. One parameter is the temperature, another parameter the critical current, and the third parameter the external magnetic field. Okay. Now these three parameters have to be taken into consideration. For example, let me see here. We want to have a magnetic field of 5 Tesla. Okay, this is the 5 Tesla here. So we have this 5 Tesla. Okay, for the 5 Tesla, if I operate at 4.2 Kelvin, that is here is the temperature, 1.9 is somewhere here, and 4.2 is somewhere here. So if I operate at 4.2 K, you can see very clearly that the field what it can produce is smaller. It's not the same. Okay. The field what it can have, maximum field it can have is smaller. Whereas if I reduce the temperature to 1.9 Kelvin, then the magnetic field what it can produce at this value is higher, which means that it has a higher critical current at lower temperatures. Okay. For example, the critical current at 5 Tesla at 4.2 K is around 3000 ampere per millimeter square. That's the critical current. Whereas if I go to 1.9 Kelvin, this value can go to almost about 10,000 amperes per millimeter square. Okay. So this is for niobium titanium wire used in Large Hadron Collider, the courtesy by L. Botura of same. Okay. Now there are two types of superconductors. There is a low TC superconductor, there is a high TC superconductor. The materials having the critical temperature below 25 K is known as low TC superconductor. The materials whose critical temperatures are above this 25 K and close to liquid nitrogen temperature, they are known as high TC superconductors. Okay, for the low TC superconductor examples are niobium titanium, niobium tin, etc. So the maximum value is somewhere around 23 Kelvin. Okay. They require liquid helium as the coolant. In 1986, Bednarz and Mullers, they discovered the oxide-based superconductors. They were studying experiments on resistivity on oxides, and they found that ytterbium barium copper oxide, YbCO, or for example, BISCO, etc. There is superconductivity in these oxide materials, and this happens at a temperatures close to liquid nitrogen temperature. So the TC values are somewhat higher, okay, around 100 K or even more. So superconductivity can now be obtained by using liquid nitrogen instead of liquid helium. And here also, as in the earlier case, the superconductivity is followed by Meissner effect. The Meissner effect is the expulsion of magnetic field, or in other words, the material becomes totally diamagnetic, a perfect diamagnet, right? That's what happens. Okay. What are the applications of superconductivity? There are a whole lot of applications of superconductivity for making magnetic resonance imaging magnets, NMR, tokamaks, etc. So there are a large number of applications for superconductivity. Superconducting RF cavities for particle accelerators was in the area of superconducting magnets, Tavatron, Hira, LHE, etc. Then it also become very useful for magnetic levitation, in other words, transportation. Because then in that case, when you might have, I don't know whether you have seen the video, the magnetic field, due to the magnetic presence of the magnetic field, okay, the material floats on the surface because the material become perfect diamagnet, so material floats. on the surface. If possible, I'll try to show you the video today. Okay. Okay, there are other applications like superconducting quantum interference devices, squids. Okay, they are also, squids are very useful for measurement of magnetic fields of extremely small values. Okay. Okay, now the superconductivity is a field where a lot of growth has been seen. High field magnets for MRI, NMR, etc., are made of superconducting magnets. They are fabricated by low TC superconducting cables, and the low TC superconducting cables they look like this, as you see in the picture. You take one of the strand, and then if you enlarge it, it will look like this. And this is still a closer view. So what is all this? It is actually copper matrix in which these are all superconducting wires. So this whitish thing, what you see is actually the superconducting wire, and then the surrounding is copper matrix. So now this is actually done by starting with a billet and then keep on reducing the billet in size and then drawing the wires. Like that it is done. Okay. Now they are fabricated with the low TC superconducting materials. Now if you want to use them, then you require, if you want to use them for magnet applications, then you have to reduce the temperature. For reducing the temperature, either you have to use liquid helium or two-stage cryocoolers for the specific applications of cooling. Okay. The cable is actually shown, superconducting cable is shown here. This picture shows you the superconducting magnets built out of low TC material. Typical superconducting magnets, they use normally liquid helium as the coolant. Sometimes one uses also liquid helium cryostat along with the recondensation system. Okay. This recondensation system can be a cryocooler. That means evaporating vapor is recondensed and then falls back into the magnet itself. Okay. Nowadays, we have also systems what are called dry magnet system, wherein you can generate a magnetic field. You can start with a superconducting magnet, which can be cooled by not liquid helium, but by cryocoolers. So the temperature keeps on decreasing, and then when it goes below 5 Kelvin, then you can charge this magnet, etc. So it can be useful as a superconducting magnet, but does not have liquid helium. These dry magnet systems only use cryocoolers for cooling the superconducting magnets, and they are really advantageous. Okay. These are special cavities for particle accelerators. They are made of niobium. So have the beam vacuum inside. It should be separate from the insulation vacuum, and it is surrounded by a bath of liquid helium. And it is designed for all shapes and various frequencies, 80 megahertz. And typically, it looks like a bulb. Okay, so it has the shape of like this, you can see. Okay. And it has a high beta elliptical shape. Okay, the magnetic levitation is another important aspect. I don't know that it will play here. Not sure. No, I think it's not playing. Okay, we'll play this separate. Okay, the magnetic levitation is what is called the Meissner effect. Due to the flux winning, the effects, a magnet can be held over the superconductor. By the same effect, magnet also lifts the superconductor. They are useful for the electromagnets. One can also use electromagnets in place of conventional superconducting magnets. Okay, the application would be for high-speed trains, that is without any friction, zero friction, and then it becomes very useful. So we have programs what are called magnetic levitation or maglev. Okay, programs are all there. The SQUIDs or superconducting quantum interference devices. The SQUIDs consists of two superconducting materials separated by oxide layer in between. Then the electrons can now tunnel from one superconductor to another superconductor. And this tunneling is characterized very interestingly. So now you have a loop. The superconducting material is there, and then you have an oxide layer. So this loop of superconductor can hold a certain number of, what shall we call, it has only a certain number of fluxes. It traps a certain number of fluxes. Suppose if there is a program, if there is some external agency to vary the flux, okay, let's say you pass a current in a conductor and that tries to vary the flux, then what happens? The superconductor adjusts such that it gets back to the same old flux. In other words, you will see that the current flow will have always a jump, okay, for every flux element. So that's what happens. So in other words, it is more like a flux detector. Okay, it can be used as a flux detector. So there are a lot of application areas. Specific application areas will be magnetoencephalography to monitor the brain signals, and then you can also use it for detection of magnetic field. So our magnetic field sensor. DC low DC SQUIDs operate at 4.2 K, and therefore they require liquid helium, whereas high TC SQUIDs can operate at LN2 temperatures. Right. Okay, now I am coming to the composites which are useful in cryogenics. It is a material which is created with the fiber element in a resin matrix material. So what is the composite? Composite, you have two elements. One is the fiber, another is a resin, and the fiber is reinforced in a resin. So such a thing is called composite. The constituents retain their identities, but they act in total. What are the fibers? Fibers are generally filamentary materials, like material like E-glass, S-glass, Kevlar, alumina fibers, carbon fibers of different types. These are some things which are generally used. And then the resin, as far as the resin part is concerned, epoxy resins are normally used, and they refer to a broad range of epichlorohydrin-based resins. And you can also use additionally catalyst curing agents are also used, so that by this catalysis you get the total material. The polymer resins are also mostly cured by heat or catalyst, There are also something called thermoset type. That means with the temperature, they get to a setting. Okay, composite materials many times are useful. They meet the stringent requirements that metallic materials cannot do. Now we'll see the more details. In other applications, composite technology offers improved performance, sometimes even at a lower cost. The main advantage of composite material would be low thermal conductivity, high strength, stiffness, lightweight, usable down to 1.8 Kelvin, tailored structural efficiency, dimensional stability, close tolerance, improved insulation, corrosion resistance, and minimum flaw propagation, etc. But the disadvantage will be the lack of composite material database, cost of materials. They are pretty expensive, complex design parameters, and manufacturing process. These are some of the disadvantages. Okay, let's come to the individual component. We'll start with fibers, right? Okay, fibers provide generally primary load characteristics. They provide the primary load carrying behavior characteristics. There are some very good, excellent fibers are available. And the quantitative data at cryogenic temperatures are not there. Normally, the strength of the fiber increases when you use it at low temperature. For example, 83 Kelvin, suppose I use, it increases by 54% strength increase, tensile strength for E-glass, whereas 80% increase there for S-glass from the normal room temperature value. Looking at the cost, there are cost variations. E glass is the lowest, S glass, then medium strength, low modulus carbon fibers, Kevlar, then high modulus carbon. So they are in increasing order of cost. Alumina fibers are the most expensive. Okay. Other carbons are all normally in the intermediate price range. So E glass, S glass, medium strength, low modulus carbon, Kevlar, then high modulus carbon, then alumina. So as you go on doing like this, you are in the increasing order of price, right? Okay. I think the properties are listed here: tensile strength and modulus, tensile modulus, density is mentioned. These values are for at room temperature, 295 Kelvin. Okay, coming to resins. What is the function of resin? The resin binds the fibers in the proper position and distribute the load between the fibers, protect them from abrasion and environment, and provides interlaminar shear strength. Okay, so these are the advantage of the resin. Now the failure to contraction and of the most of the cured epoxies are quite low. What does it mean? It means that if you have suppose you have a cured epoxy and there is a contraction takes place because of low temperature, the failure that happens is very less for such materials. Okay, they provide good cryogenic performance. They have a structural excellence, but at low cost. Okay, epoxies are better than polyesters in resisting moisture and environmental effects. Tensile strength and other mechanical properties normally increase at low temperature. So I think here again, the properties of thermoset resins are given at 295 K, material tensile strength, tensile modulus, tensile failure strain, flexural strength. So various numbers are given here, and then including properties like outgassing, low mass loss, collected vapor, collected material, how much it is there, and water vapor, etc. All these things are listed out here. Okay, these are done for different resins: thermoset resins, amine cured epoxy, anhydride cured epoxy, and then vinyl ester, etc. Okay. Now laminates. What are laminates? Laminates are already pre-prepared, epoxy, pre-prepared composites. The cryogenic composites are typically fabricated by wet winding of continuous fiber embedded in resin. Keep on winding. Okay, winding pre-impregnated tape or laying up and performing woven fabric, or by injection molding of the thermoplastic resins containing discontinuous fibers. Now, normally what you do is at the end of the process, you follow a temperature or pressure cooling process. You do a temperature, then you slightly raise the temperature, then the system gets cured, then you have the final product available. Now, the mechanical properties, most of them are available at room temperature, but what is known is that the tensile strength and other mechanical properties generally improve at low temperature. Okay, and this table gives you the properties, composite properties prepared with the glass, S glass, Kevlar fiber, all those various different, the fibers. Okay, this is what is normally used is 60% volume percentage is continuous fibers in the epoxy. That means 40% is resin and 60% is the fibers. So what is seen here is, for example, the thermal conductivity and the maximum stress are plotted here. And for different fibers, okay, you have three locations are shown here. One is 295 K, okay, and then 75 K, and then 4 Kelvin. So the 4 Kelvin part is actually at the bottom. 76 Kelvin is in the middle, and the room temperature is on the top. So as one can see here for different materials, the 4K value is always low. That means the thermal conductivity of the composite is lowest at 4 Kelvin. Okay, it is somewhat higher at 77K. The highest value is at room temperature. Again, in this graph, you can see the maximum stress versus the number of cycles. I think this is the fatigue. The maximum stress for different glass materials are shown here. So as the number of cycles increase, the strength keeps on going down. Okay. Now, performance at cryogenic conditions, cooling generally improves the mechanical performance, but the data is limited. The strength of, normally one uses what is called the G10 grade. Okay, G10, CR grade, its strength improves by 100%. And the modulus also by 30% from 77 Kelvin to 4 Kelvin. Compressive strength again improves. It increases from 295 to 20K by almost 55% for S-class, 27% for Kevlar 49, and 33% for carbon composites. Okay. For the filament formed composite material, the tensile strength increases by at least 30% when cooled from 295 to 76. So what you notice here is the performance of the composite at low temperature is certainly better. Okay, what are the failure mechanisms? There are basically 4 failure mechanisms one can think of. The layer can crack. Then delamination, that means one layer can separate to another layer, so delaminate. Then fiber sometimes can break. And then fiber to matrix, the resin matrix to debond. Okay. Normally, the fatigue strength depends on basic materials, fiber orientation, composite quality, test specimen configurations, etc. Whereas higher modulus fibers provide normally a better strength. So fatigue performance also improves at cryogenic temperature. That means the low temperature gives you a better performance. Okay, and sometimes one can also compare it with the metals, their performance. They are done by what is called ratio critical values. Okay, low ratio of thermal conductivity to strength. What it means is thermal conductivity is lower compared to the strength. Low ratio of thermal conductivity strength. It means it can improve the system performance and reduce the cost when components are subjected to low temperature gradients. Composites certainly have certain advantages. Suppose you think of high modulus to density. Okay, it reduces the weight and hence also the load on the equipment. So E-glass composites compare very well with that of steel or aluminum, but the strength to density ratio is twice that of steel and 5 times that of aluminum. So these are the comparisons. Okay, now what are the application areas? There are a large number of application areas. Cryogenic fuel tanks. See, we are talking about the space missions and so on, right? Now, ISRO is using the cryogenic tanks for storage of fuels, oxidizers. So for that, you can use these type of materials, composite materials, for fuel tanks, for liquid hydrogen, instead of aluminum tanks. The typical tanks are 5 mm thick and 2.5 mm, 2.5 meter diameter and 4.9 meter height. Carbon epoxy tanks are reusable. They are also can be used, and they are also useful because they can be thought of as reusable launch vehicles. Now, GR10 type composites are used for supporting. They are to support the inner vessel and insulate the liquefied LNG tanks. They are also used for supporting a vacuum insulated LNG fuel tank or trucks, buses and trains, etc. Now, filament wound straps are utilized to provide structural support for thermal isolation cryostats. Composite straps are used in magnetic resonance imaging and magnetic energy storage system. On space shuttle, Hubble spacecraft, cosmic ray background explorer, etc. can be used. Now, generally, they are useful as neck tubes. Okay, you can use as a neck tube from room temperature to low temperature. The composites tubes can be used for this purpose. Okay, re-entrant posts are also developed by Fermilab for superconducting dipole magnets and GR10 nested systems, right? I think here gives you a photograph of couple of materials. So you can just have the tube, neck tube. They are also used, for example, in liquid helium cryostats to make sure that this is actually kept inside the liquid helium neck, Dewar neck, such that the evaporating vapor goes always very close to this, the metallic neck, metallic part, this tubing is useful so the gas flow happens between the metallic and this one. And then you have a heat transfer, you have a cooling due to the very close radiation shields are getting cooled by the evaporating vapor. Okay, I mean, you can see the liquid hydrogen tank. Okay, composite support straps. Nested components tube with heat intercepts here. Again, composite neck tube with stiffening rings. And this one you can see here the different shapes and sizes of the tubes, neck tubes. Okay, there are a whole lot of references available. Okay, on cryogenic databases available. So that is all listed here. Okay, and that's all. I have to stop talking. So thank you very much for your patient listening.